good morning, good afternoon, good evening, everyone, depending on where in the world you're joining us. I'm Jarka Glassey. I'm the president of the European Federation of Chemical Engineering. I have taken on the role of the president in January 2026, following 2 terms on the board of EFCE as the vice president executive. I'm a biochemical engineer by education. I graduated from Slovak Technical University in Bratislava, but I worked all my professional life as a professor at the University of Newcastle in the UK, recently taking an early retirement from there and engaging with other universities around the world much more. Although on the program you would have seen that my colleague Bulos Hur was going to do the introduction for this webinar. Unfortunately, for personal reasons, he can't join us, so I'm very happy to be involved with the introduction of this webinar on why spray drying keeps us busy, the science behind continuous innovation, and I'm really looking forward to hearing a lot more about it. Let me first say something about the Spotlight Talk series. This is now our 6th year of the Spotlight Talk initiative, which started in 2020 to keep together the community during the COVID pandemic. The success of the previous years convinced us to transform the Spotlight into a regular feature of the EFCE program. So we now have 1 series in odd years and 2 in even years like this year. This spring, 11 of our working parties and sections are delivering over these 2 weeks 9 webinars of 3 or 4 talks focused on specific topics by leading industrial and academic experts. The series also enables attendees to sample matters in new areas, encouraging cross-fertilization of interests. And if you haven't registered for the full program, you can have a look what else is available. The program is available on the EFC website, and you can also find recordings on our YouTube channel. A little bit more about the EFCE. So EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 chemical engineers around Europe. EFCE's working parties and sections cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of our activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. This year, EFC introduced a new initiative, virtual coffee meetings with the president, so that we can discuss how we can strengthen our collaborations with colleagues. These meetings usually take place every 3rd Thursday of the month, with some of them being dedicated to member society representatives, and they would have heard over email about those, and some open to anyone engaged with EFCE. And for those, you can find links to register on our website, so do please pop in. I am sorry we can only do the virtual coffee, but at least we can have a discussion how best you can engage with us. So before concluding, I would like to thank all of the colleagues who worked hard within the working parties, sections and wider EFCE for this initiative to happen and to be successful. In particular, many thanks go to our EFCE's Maarten Poo in Toulouse. Thank you so much, Maarten, because she did most of the conceptual setting up and practical activities as always. I thank you for your attention and I wish all the speakers and the attendees a fruitful and successful webinar. And I will now hand over to the chair of the working party on drying, Mr. Maarten, I apologize, Maarten Schutyser, to start the webinar. Thank you, everybody, and enjoy.
Thank you very much for your kind introduction, Jarka. So welcome also on my behalf. My name is Maarten Schutyser. I'm a professor at the Laboratory of Food Process Engineering at Wageningen University. And my expertise revolves around drying and dense food processing. In that sense, I'm, let's say, representative in the working party drying and also currently the chair. The mission of the working party and drying is in fact to involve, let's say, experts in drying technology from different EU countries And our mission is in principle to promote science, technology, and education in the field of drying technology. And we really stimulate interactions between academia and industry, and also stimulate, of course, the interaction between the experts of different EU countries. And for that, we do that, for example, by now physically organizing, for example, the Euro drying conferences. And so the next Euro drying conference I will announce at the end of this webinar. But we also promote, of course, EU representatives and people in the field to join other conferences like the International Drying Conference. And I'm also very happy that we organize these spotlight talk also today. So also with the help of the general EFCE organization. The previous one was on electrically driven dewatering and drying technologies. It was a very great, also well attended spotlight lecture, because also you don't have to travel. You can just follow the webinar behind your desk. I think that is a very nice way also of involving speakers from many different countries. And I will share now the presentation to introduce the spotlight of today. And I'm very happy that this time Professor Katarzyna Samborska organized the webinar of today. And she will explain more about the motivation, why she chose this topic to choose today, and why she selected the speakers that have been invited for this presentation workshop. So, Katarzyna, if I can give the floor to you.
Okay, thank you for the introduction. Yes, I have to explain you my motivation why we are meeting today under this topic. So I'm affiliated at Warsaw University of Life Sciences in Poland, and why I work here under about, of course, spray drying. And of course, we all know that it is not very new technology. The history is quite long, like 150 years. So you may say, some of you may say it's quite easy. Yes, it's nothing special. It's just atomization, just the contact with hot media, evaporation, and collection of the powder. Yes, it's true. It's quite easy. But on the other hand, when you enter any scientific database and you search for this term, spray drying, you will see that the number of publications is really huge, which are still published. So without time limit, it's about 2 million in Google Scholar. But if you limit it to last 5 years, it's something like 19,000 of papers which were published, and they are still appearing. So I think that some people think around the world that this history is still not finished, and it's also my opinion, and I hope it's also opinion of the experts which are meeting today here, because I invited them, and I'm very grateful that they accepted my invitation. So they will say their opinion, why they think it's still important to work on spray drying, what problems can be solved, what are the motivations for these modifications. And I think that it can also be important if there are any more problems which are appearing during the investigation, because I cannot believe that we can solve everything. So I'm very curious to listen to these presentations, and I'm sure also that participants of the webinar also are some authors of these publications, which we can observe they are being published. And I'm grateful also for these registrations and the people who are listening. So please, I think we can start. We'll listen to the first speaker. So it will be Dr. Alicja Ska-Dołomisiewicz from the same university as I am from the same lab, from the same spray dryer, we can say. So Alicja will start, but please remember that we will have 25 minutes of the presentation, and after then 5 minutes for questions. So for the participants, I would like to ask not to talk, not to interrupt during the speech, but after you can raise some questions or you can write them in the chat. So Alicja, please, the floor is yours.
Of course, I am sharing my screen right now with you. Good morning, good afternoon, good evening, everyone, obviously, all around the world. Hopefully you can see my presentation already in the presentation mode. My name is Alicja ska-Dołomisiewicz, and I am representing the Department of Food Engineering and the Institute of Food Sciences at the Warsaw University of Life Sciences. I am a proud member of DASD team along with Professor Katarzyna Samborska and Dr. Jedlińska. And today I will walk you through what we are doing and what we are working on, which is air dehumidification and dehumidified air assisted spray drying. So to start, spray drying is the most widely used technology for production of food powders because it easily converts liquid into a stable form. However, as me personally and we as team are working in food area, what is important for us is that our matrixes, our raw materials are mostly fruit juices, vegetable juices, molasses, honeys. So the raw materials that contain quite a significant amount of low molecular weight sugars and organic acids such as fructose, glucose, malic acid, citric acids. And these compounds characterize with low glass transition temperature. When they are present in a significant amount in these materials, they will lower the overall glass transition temperature of these materials. So this will really be a severe issue in the food industry, as it will create the stickiness problem during spray drying. So the powders will adhere to the walls of the equipment inside the drying chamber. They will agglomerate, stick to each other, conglomerate, and at the end, they will exhibit low powder recovery and quite difficult physiochemical properties to work with then in the industry or as for the consumers. So to understand the origin of the stickiness problem in spray drying, I would like to quickly tell you a bit about it. So it is basically essential to discuss the concept of glass transition temperature. So this is the temperature, the point below which we will observe the material in its glassy state, so the desirable state. It will be brittle, it will be, in the case of powders, it will give us the free-flowing powder. And if the material really reaches the temperature above this point, so glass transition temperature, we will observe the rubbery state. So we will see that the material is soft, it is flexible, it is syrupy-like, so we won't get this free-flowing powder that we can easily work with. And definitely it will cause the problems with the powder recovery as well, as I mentioned. So what are the solutions normally in the industry, and what is our solution as a team working at my department? So to understand a bit more about how and when we observe the stickiness problem, I would like to present you this short graph figure where you can see that generally when we do not have any carrier in the powders and we have, let's say, ambient or even high humidity of drying air, we observe the stickiness, let's say, in the zone over to 20 Celsius degrees above the glass transition temperature. So if the material reaches this zone over 20 Celsius degrees over the glass transition temperature, we will observe the problems. The solution to it, especially in the industry, is to add carriers. Carriers are the high molecular weight sugars, mostly polysaccharides and proteins. So when they are added to the raw material, they increase the overall glass transition temperature. So we move this point, the problematic point, so glass transition temperature, and we ensure that we are not reaching this zone where the stickiness might occur. However, normally in the industry, to achieve this effect, especially working with ambient or high drying air humidities, the carrier content is quite significant, around 50% of solids of the material. So what is our solution? What we are working with is lowering drying air temperature. When we lower drying air humidity, it is possible to lower drying temperature. So we are ensuring that we are not reaching this point where we can observe the stickiness. At the same time, we can lower the carrier content or even eliminate it completely, because we don't it is not necessary right now if we are lowering the drying temperature, because we are moving this point a bit lower. In the concept of dehumidified, basically the air dehumidification is not something new. It's not the new concept. It is commonly used in the industry, in the research. However, the air dehumidification as a way to lower drying air temperature is quite, let's say, a new concept. It was presented by Professor Samborska and Dr. Jedlińska in 2019. And as you can see over here, we have the comparison between traditional spray drying, SD, and dehumidified air-assisted spray drying, DASD. And in the traditional spray drying, the drying air humidity is around 7, 8, 10 grams per cubic meters, obviously depending on the external conditions. And the standard spray drying temperature is around 100 Celsius degrees at the outlet. At the inlet and at the outlet, it is around 80 Celsius degrees. And due to air dehumidification, when the drying air humidity is lower than 1 grams per cubic meter, the inlet air temperature can be lowered to 80 Celsius degrees and the outlet to 50 Celsius degrees. So you can see that the difference and the temperature drop is quite significant. And why it is possible to manage and to have satisfying course of drying when the air humidity is lowered, by this modification, we increase the driving force of mass transfer in spray drying, so it enhances the evaporation rate of water from the feed solution. And as for the integration of this technique to traditional spray drying, it is just the extra unit, the air dehumidification unit, that is added to the traditional spray dryer. Over the years in the research, you observed that air dehumidification was used to dehumidify processing air. And as you can see, over here, we can see few different methods to dehumidify processing air. It can be either used as adsorption phenomenon or condensation phenomenon, or for example, as we are working at our department, it can be both condensation and adsorption phenomenon. So what actually air dehumidification can solve the problems that we encounter with traditional spray drying. So by decreasing air humidity of inlet air, we are ensuring higher driving force for water evaporation. So in consequence, we can reduce drying temperature, and then we can reduce carrier content and or eliminate it completely, which I will show you in a few of our case studies. And what is the effect of all of it? We can reduce the stickiness problem. This is the most important thing, so we can ensure a satisfactory powder recovery, and we can omit the problems that we can have then with handling of powders. In some cases, powder recovery that we observed in these studies was very high, even over 90%. With lowering drying air temperature, we can as well observe lower thermal degradation of bioactive compounds, which are quite present in the materials that we are working with. So fruit juices, vegetable juices, concentrates, etc. And as well, by lowering the carrier content or removing it completely, we can propose to consumers clean label products. And they are right now quite interested in these types of products, as they have more knowledge, the consumers, and they are really paying attention to what is in the formulation of the final product. In this part of the presentation, I'd like to illustrate the potential of this technology by using several examples and case studies. And I will start with the studies that were performed on honey. Honey was spray dried using, in both of these studies, using traditional method as for comparison and using obviously the dehumidified air assisted spray drying. Once again, I would over here like to underline over here that usually in the industry, specifically with honey powders, we know that 50% or even 60% of carrier per solids is added to the powder. So it is quite a significant amount. And over here in these both studies by air dehumidification, we could lower the drying air temperature. So it was possible to lower the carrier content even down to 20%. And at the same time, which was very interesting, we observed a very high powder recovery, over 80% or over 85%. At the same time, over here, as you can see at the bottom in this blue frame, these powders that were produced, they obviously were free-flowing, so we did not observe any problems with their functionality. However, they characterized with quite low glass transition temperature from around 7 to 20 Celsius degrees, but after spray drying, after producing them, at the same time, they presented appropriate water content, appropriate water activity, and satisfactory flowability. And water content and water activity, when they are satisfactory and appropriate, they ensure the powder's stability. Continuing with our work, the idea of eliminating the carrier completely appeared. So the first study that was performed with no carrier was pure kiwi berry pulp, which was spray dried using, in comparison, traditional spray drying using high temperatures, and as well the dehumidified air assisted spray drying. Due to the composition of the materials, because obviously sometimes I will show you in a second, sometimes it is possible to reduce the carrier completely, but sometimes not. It really depends on the materials composition. Over here, due to the high content of pectins in the kiwi berry pulp, it was possible to reduce the carrier, eliminate the carrier completely. And at the same time, as you can see, with no carrier due to air dehumidification and due to low drying temperature, we noted very high powder recovery over 75%. With sour cherry juice concentrate, which is a very difficult material to be spray dried because it contains significant amount of low molecular weight sugars, but as well high content of organic acids. Over here, it was not possible to eliminate the carrier completely. However, it was possible to reduce it significantly, especially in comparison of what we could observe in the studies over the years on sour cherry juice concentrate. Normally, it was 50% of carriers per solid, but by reducing the air humidity and drying temperature, we reduced the carrier down to 30%. And with maltodextrin as a carrier, we noted the satisfactory powder recovery over 50%. So what can be taken from these studies so far is that we eliminated the stickiness problem due to air dehumidification. As the data that we observed from eliminating the carrier completely, the idea of exploring more materials and see how they will react by removing the carrier using this technique. We as well spray dried the cloudy beetroot juice at lower temperature, which was 130 degrees Celsius. We could as well remove the carrier completely. And over here, once again, we noted very high powder recovery, over 85%. We continued the studies, and we studied the purple carrot juice concentrate, mango puree, black carrot juice concentrate, and sauerkraut juice as well. And we managed to produce powders. Some cases, the powder recovery was not that satisfactory, but that was due to, especially for mango puree and sauerkraut juice, due to low content of solids in the feed material, and as well in the case of sauerkraut juice, due to a very significant content of the organic acid. But as you can see with the concentrate, it was possible to produce powders with very satisfactory powder recovery without any carriers. Over here, I would like to discuss one important issue, one important thing, because we are working with food materials. And in our case, juices, concentrates, vegetable pulps, etc., they are potent with bioactive compounds, and they present antioxidant activity due to the components of these materials. And what I would like to show you over here is that in 2021, a new way of calculating retention was presented, because the loading and retention is not the same thing. As you can see over here in this red frame, this is the total phenolic content of white mulberry molasses powders, and with increasing carrier content down to 10%. And as you can see over here, due to increasing the content of molasses, the total phenolic content increased, but at the same time, when we were calculating the retention coefficient in a new way, we noted that there was no significant differences between the variants. This type of calculation, this retention coefficient, it allows to exclude the carrier from the calculation. That is why we can directly compare the degradation of bioactive compounds in the powder and with the raw material prior spray drying. That is why it is, in our opinion, so important to take it into consideration while definitely expressing the retention coefficient, eliminating the carrier from the calculations. Despite the advantages of this technique that I presented to you, obviously there are some limitations and there are some issues that we have to think about. I would like to start with the dependence on external conditions, as this process can be sensitive to external environmental conditions because we are using air dehumidification. As we are working with air dehumidifiers, they have their limitations as the equipment. And if we really intend to lower the drying air humidity below 1 gram per cubic meter, or even to 0, if we know that the weather was not really favorable that day and it was raining and the air humidity of external air was quite high, it wouldn't be possible to lower the air humidity to that really low level. That is why over here that is a quite a limitation, dependence on external conditions. Secondly, the implementation of air dehumidification system definitely involves additional equipment costs, which has to be considered, especially for the industrial application. In a second, I will talk a bit more about energy efficiency, storage, and retention coefficient, the problems that we observe, or the issues that we see with retention coefficient with dehumidified air spray drying. In this research, the buckwheat honey was spray dried with two different carriers, maltodextrin and skim milk powder. The honey was spray dried using traditional spray drying, SD spray drying, and using this technique of air dehumidification, so DASD spray drying. And in this research, we verified how the energy consumption, specific energy consumption and energy efficiency changes due to the change in the method. And as you can see over here in this red frames, when DASD method doesn't matter the carrier if it was maltodextrin or skim milk powder, as you can see that energy consumption and specific energy consumption increased significantly. And at the same time, energy efficiency significantly decreased. So definitely these parameters such as energy consumption and specific energy consumption, in the case of DASD, we observed the extra energy expenditure, which was related to extra unit to air dehumidification. And especially for the implementation in the industry on the industrial scale, the application has to be really carefully deliberated because we can observe the low energy efficiency, but at the same time, we know that there are very important benefits such as increasing the content of this raw material in the powder, so increasing as well the antioxidant activity of the powder and its potential in bioactive compounds. But as the disadvantages over here, you can see the energy efficiency is quite low. With the retention coefficient, the something that has to be studied more is definitely how the dehumidified air influences this parameter. So in the case study on sour cherry juice concentrate, where different dairy byproducts were used as carriers, we used chromatography to verify the bioactive compounds content in the powder in comparison with the sour cherry juice concentrate. And what we can say right now is that not every time lower drying temperature will mean higher retention coefficient, because as you can see over here on the right on these figures with polyphenolics and flavonols at the bottom, you won't see any really significant differences with retention coefficient. It doesn't matter the carrier content or drying method. So this really highlights the complexity of the drying process, of the spray drying process, and definitely this problem why there is the need for further systematic research. Definitely what really happens during the spray drying, that even though we are lowering the drying temperature, why we do not see the higher retention coefficient, especially when we are excluding the carrier from the calculations. One last thing that I would like to mention is the storage. It is a very important issue, especially for then handling the power. So obviously, when the amount of the carrier is reduced, the additional challenge may arise during storage because powders with lower carrier content may be more prone to caking due to the water absorption. Water characterizes with very low glass transition temperature, minus 135 Celsius degrees. So if the powder absorbs the water, the overall glass transition temperature will decrease and we'll observe caking and problems with handling. So definitely the storage conditions and packaging must be well thought of in the case of especially powders with reduced carrier content. But what has to be studied more as well, because we do not observe right now lots of studies performed with air dehumidification in spray drying, and then how it influences the physiochemical properties of powders and how then they behave in the storage. So this is something that has to be studied more, how to then properly store the powders and how the process really influences the storage conditions and the packaging and the properties and handling of powders. I would like to mention one last thing, the industrial application. What we know from the literature about application of these methods, so air dehumidification system, we know that in 2 dairy cooperatives in Europe, in the Netherlands, in Poland, they for quite some time, they are using air dehumidification system for their spray drying towers. However, what we do not know from the literature is that if they are really using it to lower drying temperature. Most likely they're using it to control the humidity of drying air, not necessarily to modify the drying parameters. And as you can see over here, we do not find the literature on application of air dehumidification in, let's say, production of fruit powders, vegetable powders, so the sugar-rich materials that are really difficult to be dried. To conclude this presentation and the research on dehumidified air-assisted spray drying, I would like to underline the most important thing that should be taken from it is that this technique resolves the issue of stickiness of food powders, and at the same time it ensures very high powder recovery, in some cases even over 90% powder recovery. Due to lowering the drying temperature, we observe the lower thermal degradation, which is not of bioactive compounds, but it is not the same as retention coefficient. But what is really as well very important, that due to lowering drying temperature, we can lower the carrier content and increase at the same time raw material in the powder. So we can increase the bioactive compounds potential in the final product, which would not be normally achieved using traditional spray drying. So that is very important. And due to that, DSD creates the possibility for production of functional clean label products that are right now quite popular on the market. But at the same time, extra energy expenditure has to be taken into consideration, especially for the industrial application, because we have this extra unit and this extra process of air dehumidification. And as I already told you, with retention coefficient, we know that not every time lower drying temperature translates into higher retention coefficient, and the research on this matter has to be studied more. And this is the end of my presentation. Thank you so much for listening, having me, and I am open for a discussion.
Thanks a lot. It's time for questions. You could see that really some people are very busy with spray drying. Still need a lot to be done. Do we have any questions? If not, maybe yes, something in the chat. Alicia, can you see it? I can read.
Yes, I can see that there is, what is the impact on the spray dryer capacity? It comes to the extra application of the unit or the capacity of the spray dryer itself, right? We are working with the pilot scale spray dryer, so the capacity of it is on a pilot scale. However, I don't know if I understand this question correctly. Maybe Maarten will help.
Yeah, maybe I can explain a little bit. Yeah, so if you go down into temperature, then yeah, usually you also decrease the capacity of your by just you have to lower your feed, let's say. And yeah, that can have quite a dramatic effect, I think. But do you have some figures on that? So
you mean how we adjust, for example, the liquid feed, pumping, etc., etc. There was the initial preliminary studies performed. I was not involved in that part because I was still a student. However, Professor Katarzyna Samborska worked quite a lot about on it with our spray dryer. And right now we are using the parameters that were back then tested. And for example, we note that to ensure the really efficient drying, we have to remember about 50% concentration of solids in the liquid feed. And in this liquid feed, then we will reduce from the solid, we will reduce the carrier content, for example. So the raw material will be more significant. The same with the speed of our pump, or the same with the rotation speed of the atomizer. There were some preliminary studies done, but for example, for the industrial application, definitely scaling up. And right now, the setting the parameters right to this for this application of dehumidified will have to be studied if ever applied on the bigger scale.
And do you also pre-concentrate your juices or these type of things with a certain
yes,
evaporator?
sometimes, but not always. For example, in the case, sometimes we buy from the market already juices that were concentrated, but sometimes we concentrate them if we, for example, we concentrated, for example, the sauerkraut juice because the solids content was really, really low, so it was necessary to do it. But
and how do you do that then?
We have the evaporator, laboratory scale evaporator, and we just did the concentration process.
And the vacuum or so, yeah.
But sometimes really use just juices, the plain juices. Recently, I spray dried the juice with, let's say, a blackcurrant puree, and I did not concentrate it, and I still achieved quite an important amount of powders from the spray drying. So it really depends. We can work with both, let's say.
Thank you. I understand there's another question.
Yes, there is one more question about carbon dioxide emission, because you mentioned that the energy consumption is higher, but do you have any numbers on the actual carbon dioxide emission?
No, we did not test it, but it is something that should be considered for the future research. Thank you for mentioning. We just did some time ago, we measured the energy and expenditure, but we did not include the CO2 production. So that is something that has to be studied. Another issue to work with spray drying and to resolve. Thank you.
And we will invite the next speaker. So now we will change from modifications about the drying media to the modification of the construction about the drying chamber. So the next speaker is Juray de Wilde. The floor is yours.
Can you hear me well, and can you see my screen?
Yes, it's okay.
All right, thank you. Good morning, everyone. I will talk about the use of high G operation in combination with other things to intensify spray drying. So this project started when we were working with Friesland Campina and others on vortex chamber technology for drying and coating, particle drying and particle coating applications. I will say a few words about that so that you understand the background, and then we will turn to spray drying, which is of course totally different, and what we did to make that work. And so let me introduce what high G operation is about in the context of particle drying. That brings you very quickly to fluidization. Yeah? If you have a fluidized bed, there are limitations in the efficiency related to Earth gravity, the role of Earth gravity. You fluidize against Earth gravity. So the slip velocities are limited because of that. And as a result, also the coefficients of heat, mass, and momentum transfer. And working high G, you can, of course, increase the heat transfer coefficient, mass transfer coefficient, and so on. And also the momentum transfer coefficient, or drag coefficient, they call it. And so by doing that, you can, of course, affect the efficiency or the rate of drying processes, because they are all about mass and heat transfer. Yeah? And by making such processes more efficient, you can reduce the size of the equipment. Yeah? And another thing is that by increasing those, for example, the drag force, you can do things that you cannot do in conventional equipment, okay? And that is, for example, drying ultrafine powders, cohesive powders. They agglomerate, they stick together when when fluidized against Earth's gravitational field, so you cannot properly fluidize them. In a high G field, the van der Waals forces that are responsible for that agglomeration become relatively unimportant, yeah, because the other forces become more important. And so then you can do things that you cannot do normally. And so in drying, there are publications. I don't have the time to go through all those publications here, but we demonstrated that you can reduce the size of the equipment for same drying capacity, same drying quality, with about 1 order of magnitude. And we dried all kinds of materials. And then for coating, let me show a few slides. Sorry. For coating, this is work we've done with Campina. We were asked to coat cohesive powders, and did that in a vortex chamber. Let me explain here the functioning of the vortex chamber. You introduce gas or liquid tangentially. And so the entire device is static, but the motion in the chamber is rotational. Yeah? And the fluid is evacuated centrally here. And of course, if you suspend particles in such a rotating motion due to their inertia, what they call the centrifugal force, but it's inertia, they accumulate near the wall and they are glued against the wall, so they rotate against the wall. Yeah? And the fluid flows through the bed at very high velocities, while the particles are not entrained. So you have much higher velocities. The advantage of vortex chambers is that they are also very flexible in terms of the gas flow rate. When you increase the gas flow rate, you increase both forces, the drag force that drives that goes inward, and the centrifugal force that goes outward. So you have a very high flexibility in terms of the gas flow rates. That is illustrated in this graph. You see here a bed of polymer particles. This is the gas flow rate, and you see that the drag force and the centrifugal force are both affected by the gas flow rate. And the bed is not lost when you increase the gas flow rate. On the contrary, it becomes even more dense. So anyway, we use that principle, to go again, for coating fine particles. The problem with fine particles is that you need to work with thin slots. Thin slots, because you need to inject an awful lot of momentum for given gas flow rate. So you can play with the momentum injected versus gas flow rate injected by just decreasing the slot size or the number of slots. You inject the same gas at higher velocity, and that allows you a higher momentum, and that keeps the ultrafine particles inside. The price that you pay is pressure drop, but there is something that you have to do in order to treat such fine powders. Yeah? And so we just put a nozzle in the center of this vortex chamber. This is the vortex chamber. This is here you evacuate the fluid. We put the nozzle. So we were in fact top spraying on the rotating bed, and then varied the conditions. They are in this table, but I cannot go in detail. And try to figure out in what range of liquid gas flow rates and also what residence time we needed in order to coat the particles properly. In what range of operating conditions do we keep the bed? At too high liquid flow rates, the bed is not kept. There is too much agglomeration. But in given ranges, you can manage the drying rate so that you do not have too much agglomeration and you keep the bed fluidized. And so that we had to find out to then come to properly agglomerated and coated powder. We could play with the agglomeration just by playing with the drying flow, the air flow rate. This was dried by air. While coated, it was dried by air, and that is the gas that is fed in the vortex chamber. And by increasing the airflow rate, you dry faster, you have less agglomeration. That is what you see here. And at lower airflow rate, you dry a little bit slower and you have somewhat more agglomeration. So here you have really minimum agglomeration. We had a very fine layer deposited. You see that here. The particles were on average, I think 70 micron, and we deposited a layer of 1.2 micron on those particles, with very few cracks, to be honest, and resulting in 60% reduction of the release rate of an active component, which was fat, if I remember well. So, okay, from that, we started working on spray drying, and that is totally different application because you work under dilute conditions. So far, we focused on dense beds, dense rotating beds. And here in spray drying, you work more dilute. That has as a result that the rotational speeds in the chamber become much higher. Yeah. You can imagine that if you have a high mass of particles in there, it slows down the rotational speed, but in spray drying applications, it's more dilute and so on. The objective here from our collaborators was to reduce the size of spray dryers and, if possible, improve the energy efficiency. And we tried different concepts. We started from where we were working in coating and tried axial multi-zone operation. From the beginning, we had in mind to work with drying in two steps. A fast initial drying with hot air and then a final drying with more mild temperature air. The reason for that is that you have to very fast form an initial particle, an initial crust as we call it, because as soon as the particles are evacuated towards the periphery, they can touch the walls and they should not stick to the walls. Or if they are not dry, you will form a paste on the walls. Another thing is that those walls have to be cool enough in order to avoid stickiness of the particles. Yeah? So there is there are many constraints here that you are facing if you want to intensify spray drying. And so this didn't work, this axial multi-zone drying. And we had hot air injected through the central vortex chamber and the mild temperature air here. It didn't work because we underestimated the axial flows in such devices. You have the rotational flow like this, yeah, but then you have axial flow. So the vortex chambers here is 1, 2, 3. The rotational motion is that. We are looking from the side, so you have axial motion as well. And the reason for that is that the high centrifugal force that you have here is like a wall for the gas coming in. And the centrifugal force is a little bit lower near the end plates of the chamber, here, near the end plates. Yeah? And because the centrifugal force is lower here, the centrifugal pressure is less, and the gas, the air, immediately seeks the easiest way out, and that is near those end walls. And so you get that kind of motion. Yeah, you get motion in a secondary motion, which implies recirculations here in this chamber, and actually outward motion in the center. Not inward, but outward motion in the center. And so you have very strong axial mixing. Two problems. The central zone we could not keep hot enough, and these zones where we're supposed to have mild temperature conditions to do final drying and avoid stickiness, they were too hot. So we had to change the concept. And so this is shown here. These are temperature measurements. You can see that what the problem is. So we had to change the concept and went to the radial multi-zone dryer. Sorry, let me explain the concept here on this slide. Let me explain on this slide. Yeah, on this one. In a radial multi-zone dryer, we have again drying in 2 steps. Fast initial drying in the radial center, and then final drying simply in the periphery. The idea is to have a fast evacuation from the central zone to the periphery thanks to the centrifugal force. Yeah? And so in this central zone, how do you generate the centrifugal force? By injecting this mild temperature air in the periphery through vortex chambers. So we have mild temperature air in vortex chambers in the periphery. That generates a centrifugal force. Droplets injected in the center will start rotating and be very fast evacuated to the periphery. That is in milliseconds. Yeah. During that time, in the center, we contact that with hot air that we inject countercurrent with the droplets. And that hot air, we went up to 450 degrees C. Yeah, that accelerates the drying as well. So we have very fast drying in this zone. Now, it is not because we inject hot air here that it is hot here. Yeah? It is the drying that will determine the temperature in this zone. Yeah. So you will see that in the graphs, the temperature measurement graphs that I will show, the drying cools down this zone, and then you avoid degradation of your material. Yeah. So that is the whole idea. Fast initial drying in the center, countercurrent injection of droplets and hot air. Fast evacuation to the periphery thanks to a centrifugal force. The centrifugal force comes from mild temperature air injected in the periphery. Okay, so we tested that on a lab scale, then on a very small pilot plant scale, and then on a larger pilot plant scale. The scale-up was done through projects with RVO and ISPT and Friesland Campina, and then later Friesland Campina, Corbion, Avebe, and Givaudan as partners. And every time you scale up, you face challenges. And we try to use CFD for scale-up. It gives good qualitative information, but quantitative it is more difficult because you are dealing here with a very complex problem in fluid dynamics because of droplet size distributions and also particle size distributions as a result of that. And to model that accurately in the CFD code, CFD codes that work normally either with Eulerian description or Lagrangian, but then with pseudo particles, it is not so evident to capture correctly the drying process with the droplet and particle size distributions. Yeah. So what are the problems you face with scale-up? You have to prevent that droplets are deposited on the hot air inlet. When they are deposited there, there is a risk of fire, as after a while they are totally dry, they get burned and so on. Yeah? That's one thing. Secondly, you have to make sure that in the periphery the temperature is sufficiently cold in order to avoid stickiness. And then third constraint is, okay, the droplets, they come in, the hot air blows them back. That has to be fast enough in order to prevent those deposits, but you don't want the droplets to be blown on the injectors, on the spray nozzle tips, because as soon as those spray nozzle tips are fouled, you are gone. Yeah. So that were the things we had to face in terms of constraints on the particle droplet size. Then there is also energy efficiency and air uses efficiency. In order to minimize the air consumption, we do not have a vortex chamber over the entire length anymore. We have them here at both ends, and that allows us to also control the axial motion. You can generate a centrifugal pressure difference between those sides, and that allows you to control the axial motion. So this is what we did in this large-scale pilot plant. We have this is the main drying chamber. The hot air comes from the bottom. Here is a vortex chamber, here is a vortex chamber, and mild air injected here generates a centrifugal force, and the centrifugal pressure difference allows us to control the axial motion in the chamber. And then the hot air is injected countercurrent with the droplets which come from the top. Here is an injector. And on top of that chamber, here we have a cyclonic extension. What we name it like that, it allows us to improve the separation of particles and air before the air is evacuated via the main air exhaust, which is here. Yeah, those in the center, in order to have you need to contact efficiently the hot air with droplets. So you want a high droplet concentration. So we use 4 nozzles in parallel. We developed a sleeve, a protecting sleeve, a bit similar to what they use in commercial spray dryers. In order to prevent falling, we inject some secondary air through this sleeve to keep our nozzles clean. So these are typical measurements of a test that we do to prepare a spray drying test. We first do a dry run. We check the temperature profiles, and then we do water evaporation test. This is the radial center of the chamber, yeah, at different heights. So these are measurements at different heights. This is the radial center, this is the periphery. And you see when you inject water that indeed in the central zone, the temperature decreases. Yeah? Although you inject very hot air there, 450 degrees C, the drying determines the temperature, and the temperature is decreased. We can check like that in the vicinity of the hot air inlet, which is at the bottom, if the temperature should not decrease too much, because that implies that droplets reach the hot air inlet, and then we do not even start a spray drying test. So only if those profiles are convenient, we switch to spray drying test. Spray drying test we did with milk and maltodextrin. These are examples of maltodextrin test. We did many bad tests and some good tests in the end, then do, of course, all the analysis that it needs. We have microscopic analysis. Some we went too low in vacuum, so the particles exploded, they fragmented, but under the normal microscope you can see that we have quite spherical particles, hollow particles produced. And then we do all the analysis on those particles that you are familiar with. We do particle size distribution measurements, roundness distribution measurements, and so on. And you can see here how much of the powder is collected via the different, we have different collection ports where the powder comes continuously out. And then we have some powder remaining in the chamber. Then we have some powder collected in a downstream cyclone, very fine powder. And that is, we measure all that in order to evaluate the efficiency and the performance of this device. I'm almost out of time, so I will have to stop here. So these are indeed roundness, circularity measurements, aspect ratio measurements, and then we compare sieve analysis with diffraction measurements. Some words about it, because there is always a question about the energy efficiency. We are about 15% better than the normal spray drying so far, and we do not do any heat recovery at the moment. This is an experimental pilot plant, so the air goes out and we do not recover energy. We have electrical heating also, so all that is taken into account, but we are about 15% better than the normal spray dryer. We could theoretically predict that. This is a theoretical analysis on the spray dryer capacity, and we measured that as well. We measured feed temperatures, how much power we use, and then how much water we evaporate finally, and that's it. And we have an efficiency around 53%, I think, 53, 56%. And I think with that, I'll close because it's time for the next speaker. In the meantime, we improved the performance. I cannot show this yet. Oh, what I show you here has been published in Advanced Powder Technology recently. So you can find the details there. But in the meantime, we did better tests improving the hot air distribution. You need to have a very uniform hot air distribution in order to have symmetry in the chamber. And that is very crucial if you want to improve the performance, which we did over the past months. Anyway, I would like to conclude. There is a huge potential with high G operation. By the way, and of course I should have told that, I forgot, but so this pilot plant has about 100 kg per hour evaporation capacity, and the size reduction is about 1 order of magnitude compared to what you would have in a conventional spray dryer. Okay, so that is what I forgot to say, but which is critical, of course, for what we try to achieve. So high G operation using Vortex chambers is promising, but it's not an easy technology to develop, and there are many aspects that need to be understood. And so we are working on that for various applications, and I focused a little bit on spray drying here today. So I would like to thank many people, and especially my technician Luc Potier and all the researchers, and Axel de Broekville, my long-term collaborator, and then all the sources of financing, especially the ISPT and all the companies we worked with. Thank you.
Thanks a lot for your impressive presentation and the work also which was done. I was planning to ask about these capacities, but you have explained. Thank you. Do we have any more questions from the audience? Can you say a few words maybe how it started, this idea? It was your idea, or it was adapted from some other solutions?
Well,
from the fluidized bed, yes?
We started from the high G fluidized bed. Now, this is something, if you look in the literature, this is something that people looked at. The original idea here was to use it for polymerization because it's an extremely exothermic reaction, and you need to evacuate a lot of heat. And by having high heat flow rates, gas flow rates, you can evacuate efficiently heat. You can also improve the heat transfer and so on. So the idea was to use it for gas phase polymerization. But then looking in the literature, we found that in the 60s, there were studies to use that for nuclear applications, for space applications, and also for drying applications, agriculture. And then the research stopped for almost 30 years or 40 years. And then we had this idea, and then almost every time when you have an idea and you look in the literature, somebody else had the idea already.
Already done.
So the vortex chamber technology was developed in the 60s by the Russians and the Americans, space and agricultural, and also applied commercially, but not. I don't know about nuclear. I developed some applications with the Department of Energy, but I cannot go into detail there. But the RMD, this concept, the radio multi-zone dryer, where is it? Here, this one. That is something that we patented, and that is new.
Congratulations and good luck with future implementation.
All right, thank you. What should I do here? Stop sharing?
Yes, just.
One moment.
And we can invite the last speaker. We are just perfect with the time.
How do I stop sharing?
Maybe it will stop when the Cordin will try to share his presentation.
Okay.
Yes.
Yeah, great.
Yes. It's fine. Okay, Cordin, so the floor is yours. We cannot hear.
Yes, I'm
Yes.
unmuted
Okay,
now.
Yes, thank you.
Okay, yeah, thank you for the invitation to give a talk here at the Spotlights talk of EFCE. I'm going to talk about heat pump assisted spray drying. So I'm from the Eastern University of Applied Science in Switzerland. And yeah, this is a collaboration work of our team at our Institute for Energy Systems. We are located at the eastern part of Switzerland, as you can see here, and we have the heat pump test center in our institute where we test especially residential heat pumps for houses, for multifamily buildings, and so on. So we have quite some good network in this heat pump area and the market. And so our research activities are also built around heat pumps technology, and the industrial part is now getting more important. So the heat pumps technology will be implemented more and more into industrial applications, and this is exactly the topic of today's talk as well. So we look at how we can improve the efficiency of processes, how we can improve the efficiency of drying processes, how we can reduce the CO2 emissions and save energy. These are the major motivations, especially decarbonization and electrification of industry is now a hot topic. So first, I'd like to give you latest developments and realized examples. Then we go into some research activities at our institute and also some international view, and then some conclusions at the end. So a spray dryer is quite an energy intensive process because we need to heat up air, and this at very large airflows. So here on the left, we see here a large spray dryer, and I'm standing in front of that. So it's a spray dryer for producing milk permeate for bakeries, for example. So big, high volume products. And so we have many possible foods that are spray dried. And here we have a list from Master's book, Spray Drying in Practice, about the drying temperatures of various foods. And we see on the top, we have here 200 degree for whole milk, baby food, and so on, different products. And now, when you look at the red area, we could overlay some kind of a heat pump technology that could generate this hot air. And if we reach higher temperatures, we can cover even more such food spray drying applications. And this is actually a trend to go into higher temperatures to generate hot air with heat pump technology. Nowadays, technology is somehow, let's say, limited more to about 160 degree. That is not a clear number, but there are more and more suppliers that can reach these supply temperatures. So heat pump manufacturers that can reach it. I was a product manager for Büchi Labortechnik 5 years. This was my former job after my PhD. And now they have the mini spray dryer S300. It's a very comfortable spray dryer for lab tests with an evaporation capacity of about 1 liter of water per hour. So I think many researchers use this machine in their labs. And here we have a lot of application material from Büchi. Here also a list of possible drying temperatures for different food applications. For example, coffee in the middle at about 150 degree. It's also interesting to know. So why now integrating a heat pump into a spray dryer? And the major motivation is to save energy. So today we would have an open cycle. For example, we have here on the left some heat that is used to heat up the air, and probably 80% of it will go into the real water evaporation. The rest will be some losses, and some heat goes into the product. Now, if we can close this cycle with a heat pump, so we use the exhaust humid air as a heat source and upgrade it with a heat pump to inlet air temperature again, we can close the loop, and so the heat supply can be reduced a lot. So theoretically, this could be 80% heat recovery in such a closed loop. So this is valid for any drying processes, but especially also for spray drying processes. So what are the latest developments and realized examples? And here we have the company GA with their AddCool technology. This is a transcritical CO2 heat pump for spray dryers. So the heat pump is here, illustrated here with 2 gas coolers. They are then heating a secondary loop of hot water. The hot water goes into the air inlet line of the spray dryer and heats up the air up to about 120, 130 degree. And then on the cold side of the heat pump, there is the possibility to use the exhaust air of the spray dryer as a heat source to recover this latent heat, or to use the cold side also as a cooling or a cooling water loop. So both sides of the heat pump, the hot and the cold side, would be useful in this case. So this is an installation at the test center from GA in Søborg, so in Denmark, close to Copenhagen. And these are pictures of this heat pump that works with 2 piston compressors from GA Bock with CO2 up to 115 bar, 150 degree. And so it has a heating capacity of 90 kilowatt. So it's a pilot test setup. And so it is connected to a spray dryer, the GA MSD20, which has 1,800 kilogram per hour evaporation capacity. So with this test facility, they improved their technology, and now they have a larger system at Arla Foods in Denmark as well, where they implemented this CO2 add-on technology to also this dairy, the milk powder facility. Here you can see how this looked like. Here is the spray dryer on the left, here the heat storage tanks, and here in the middle the CO2 heat pump. This was presented by Riccardo Bergamini from GA recently in January in Copenhagen at the High Temperature Heat Pump Symposium. So the system looks like that. We have the heat pump here that produces chilled water, and then upgrades this heat source to 130 degree, which then heats up the air from 20 degree to 120 degree. And so for the rest of the air heating, there is additional steam needed and probably also electricity. So the message here is this CO2 heat pump technology manages to go up to 120 degree. The rest is still, there is still another heating technology needed. So this is at Arla Foods, integrated this GA system in a MSD 315 spray dryer, so 900 kilowatt capacity, so 10 times larger than the test facility shown before. And the total COP, so the efficiency of performance, is 3.6, which means with 1 kilowatt hour of electricity, 3.6 kilowatt of heat and cold can be produced with this system. What is interesting are first monitoring data. So this system is now running since August 24, and you see here on the left some temperature measurements over time. So where the spray dryer gets on, and here the first minutes, so probably 14 minutes is needed to get this heat pump full operational. And then after it keeps the temperature as required. So the air temperature at about 130 degree and so on. So now they estimate or they calculate how much CO2 they can reduce with this compared to natural gas. And here you see the numbers, about 1,500 tons CO2 and 670,000 norm cubic meters of natural gas. Another company which is also active in heat pump integration in spray dryers is company Lübers. They have here also the CO2 heat pumps that they integrate in a similar, let's say, concept. What is the advantage, as mentioned before, is to have the hot side and the cold side as valuable heat and cold. They reach a COP of 5.2 with these temperature conditions. This is in a larger scale, in the 6 or so 4 megawatt heat and cold. And what they use is in principle 7 of such CO2 heat pumps, and one of the heat pumps have 6 compressors. So this will be then a parallel arrangement of this heat pump installation. Here is a schematic of their system, but in principle, similar thinking steps. And then this has been integrated in a dairy in Ammerland in Dringenburg in Germany. And here you can see some pictures of these heat pumps, how they were delivered, and also the spray tower, how this looks like. And with natural gas, they would go up then to 200 degree. So natural gas is still needed to reach the 200 degree. But anyway, they can reduce or save 66% natural gas with this electrified heat pump assisted spray dryer technology. Okay, then there are other spray dryer manufacturers around the world, and here are some names, some examples. And my let's say question is there interest in heat pump technology as well from other suppliers? And yeah, just made a list of this in a table. Don't go into details here. You will get the slides later on. But more important is that the spray dryers are large, so then the reduction potential is much larger for these energy intensive processes. So here we are in the 20-ton water evaporation per hour. For example, this will be then also a large heat pump installation. Now going to the research part of my talk. I did a literature review on some modeling and simulation studies, and there is some activity seen in the research area with publications. And what are the topics that are researched? Okay, so heat recovery system, different heat pumps testing ammonia, water, so refrigerant, the working fluid studies, then different powder materials, let's say products. Also, again, here some work on working fluids and so on, heat recovery and so on. Here is a list of these literatures here on the right. And what are the results? So they typically do energy studies and economics studies. Some have here environmental studies as well, or pinch analysis as a energy analysis method, which gets more and more popular also for spray dryer processes. So we had a case study here. We have a spray dryer. We have air that comes in here in the winter, for example, -10 degrees, gets heated up in a recuperator. And then the idea would be to have here the condenser of the heat pump to heat up the air, and then probably steam or electricity to further increase the temperature of the air to 200 degrees, for example. And then have the spray dryer process, the exhaust gas, and then the recuperator and a heat exchanger, and then after the evaporator or the source side of the heat pump. So the heat pump is here shown as a black box. So in principle, it's a machine that makes hot and cold. And what's inside this container or into this black box, that's the challenge or the knowledge or what to do. What is important is to have the application information. So what temperatures, what inlet, outlet temperatures, and what capacity. And in this case, it was here 34, 19 on the source side, 80 something to 200 on the heat sink side. When we do the pinch analysis of the heating streams and the cooling streams of these processes, we have this typical curve, the composite curve, and we see that there is a big glide. So we need to heat up the air from a lower temperature to a higher temperature. It's not constant, it's a heating stream. So when we look at the black box, we would ideally choose a heat pump technology that can handle this glide or this temperature difference. And an idea is to use transcritical heat pumps. So transcritical sounds critical, but it's a thermodynamic expression that the gas or the refrigerant, in this case here propane, would be used in a transcritical state. And with that, very good glide matching, temperature glide matching is possible. So that's the major message of this slide here. And what is the parameter to investigate is in principle the working fluid in this heat pump. So in this case, propane, or here we have different other gases or refrigerants, how we call it in the heat pump community. You have here propane, here butane, for example, and some other synthetic refrigerants. And it's always a compromise between efficiency and volumetric heating capacity. So as you can see here for propane, this achieves a very high heating capacity, but the sink outlet temperature, so the achievable temperature is limited to probably 130 degrees. Like CO2 was also somehow limited to 120 degrees in the former case. With other gases, we could reach 160 degrees, for example, butane, to have that. And then this gives some compromise. Okay, so propane was found to be quite a suitable solution, but it is flammable. So would this be allowed in a spray dryer facility to have a flammable gas inside this spray dryer? That's a good question. And so CO2 is definitely also a good choice, and that's probably also the decision why the other companies use CO2. Anyway, from research point of view, it's still interesting field to use flammable refrigerants in a transcritical state. And this is what we have built here at our institute, at OST, at our university. We have a transcritical heat pump that works with hydrocarbon fluids, mixtures actually, 20 kilowatt capacity. So it's a lab scale demonstrator. Here you see the heat pump with the compressor, with the gas coolers, and some other measurements, valves, expansion valves. And here on the right, the cycle with the piston compressor, gas cooler, expansion, and the evaporator. So I don't want to go into too much detail here, but what is the main goal is to show experimentally that a mixture is more efficient for a dryer application than a pure fluid. Here on the left, you see a TS diagram. So if you are familiar with heat pumps, this is one of our main diagrams to illustrate a heat pump cycle. We have here the evaporation, then the compression, and then the gas cooling with isobutane, another flammable gas, a pure fluid, and then heating up the air or water from 100 degrees to 150 degrees. So the case would be like a coffee spray drying or something like that on the heat sink side. And you see this matches quite well here, the heat transfer. But on the heat source side, the match is not so good. So you see there is quite a difference in the heat transfer temperatures. And the goal is now to use propane and isopentane, a mixture of 60% to 40%. And here the graph shows the situation. So you see the area on the source side gets smaller compared to here. And what does it mean? So we can reduce exergy losses, the heat transfer gets better, and overall the heat pump COP, the efficiency, can be increased by this additional parameter of using a mixture of hydrocarbons. And that's the main motivation, to match the temperature glides better on the source and sink side. And this is almost my second last graph. But it shows some theoretical simulation results of this special, or let's say, hydrocarbon mixture of propane and isopentane. Here is the isopentane mass ratio. So here we have 0. So this means here on the left we have only propane R290, and here on the right it's full isopentane. And then you can see here the black curve, that's the COP. And you see a maximum, and this means at 40% isopentane and 60% propane, the efficiency is highest for these particular applications here on the right. So, and now we can see what is the benefit. If you would use only isobutane, pure fluid, then we reach a COP of about 2.6. But with the mixture, we reach 2.85. So 10% improvement of COP just by replacing the working fluid by a more optimal one. And this is the main motivation from research, and hopefully we can convince also, let's say, suppliers of heat pumps in this direction. Okay, so, but a spray dryer has typically also a fluidized bed and a vibrating fluidized bed. So we have actually two air streams that go into a spray dryer system. One is a at probably 200 degree, like for milk powder or so, drying, and the other is at a lower temperature, maybe 100 degree. So what would be then the best heat pump design? And this is the question. Is it theoretically possible to heat up air from ambient temperature to 200 degrees with a heat pump? And the answer is yes, it's possible. But we need to think about what is the best cycle design. And the proposal is to use a transcritical CO2 cascade heat pump with eternal heat exchanger. And here you see the cycle. This cycle has been evaluated by the colleagues from Waikato University in New Zealand, from Lana Kong and Tim Wamsley. And they show that this system could work with CO2 compressors that are available today with 150 bar discharge pressure. And so 200 degrees can be reached. Okay, it's a theoretical study, but we also did the model of this heat pump cycle. I know it's maybe too much into detail, but what is the message here? What is the application? We have ambient air comes in with some, I don't know, 15 degree, and then a first gas cooler from the heat pump. And then we have 102 degree air for the fluidized bed, and another part of the air comes out at 200 degree. That's the heat sink side. And on the heat source side, we would use the water from the exhaust stream of the spray dryer. And then this is probably 40 degree, goes into the first evaporator and then into a second evaporator. And with this type of cycle, it's possible here now to achieve a COP, a heating COP of over 2.5. So 2.5 something. So theoretically, and this is quite an interesting result, because the COP is also a very important economic factor for the economic calculations, because we with a heat pump which is electrical driven, this has to be compared to today's gas or fossil fuel, for example, gas boiler systems. So that's the message here, that we have some cycle optimizations that are possible. So I'd like to conclude my talk. So why spray drying keeps us busy from heat pumps view? First, spray drying is a very high energy intensive process. So we need a lot of energy. So it makes sense to look into technologies that can reduce the energy demand. Heat pump integration enables that. From theory, we can close the cycle, make closed cycle system, use the latent heat, and reduce energy consumption, and also shift from fossil fueled heating to hopefully renewable electricity heating, and this way decarbonize a spray dryer process, especially in large scale. That would be a major point. Then about heat pump technology. Today there are heat pumps available that can cover a large part of the spray drying needs, but not fully. So the 200 degree is still a challenge. So, but probably 160 degree or so is maybe today from some suppliers possible and state of the art. We have seen some realized examples from GA and also from Lübers. And here we have some data from the pilot installation and also from the larger installation at Arla, where they have some numbers of monitoring data that they can share. And for larger systems, also this, the idea to use the heating and the cooling of the heat pump simultaneously is a major benefit of these heating and cooling technologies. So typically in a spray dryer, you have a cooling stream or a cooling loop that is there to cool down the produced powder. And from research point of view, we have several areas that are active. One is for sure modeling and simulations. Then we had this optimized cycle designs. We have seen some ideas with CO2 as a refrigerant. Then this transcritical cycle and refrigerant mixtures to better match the temperature glide on the heat source and heat sink. So last one slide. This is a promotion. This is a book that I have written on high temperature heat pumps. It's in German. I'm writing a second edition. If you're interested, just contact me. At Ost, we have further education courses on industrial heat pumps. So this starts very soon again, and it's in German and in English, and it's targeted to researchers, energy, plant operators, energy responsible people. Steam generating heat pumps is a topic very often we are confronted with that. So heat pumps that can generate steam. We organized a webinar with several hundred participants, and we will do it again. So all these slides and presentations are here available on these links on YouTube if you are interested. And last but not least, I have written another book on spray drying of vaccines. So that was my Corona book, let's say. And if you're interested in this kind of topic, just let me know. So thanks a lot for your patience and for your attendance. Thanks a lot.
Thank you. Thank you for your impressive presentation. It's good to know that some of these systems are already working in the industry, but still you have some job to be done. So we are still busy with your great team. I don't know if there are any questions. It was so informative that maybe we know everything now.
Yeah.
Let's wait a second if anybody wants to ask. I cannot see.
I can ask a question if you...
Maarten.
Yeah, so thank you very much for a nice presentation, Cordin. I'm just wondering, because just coincidentally in the Netherlands, we had a full day of heat pump presentations related to drying. So one of the things that came forward was also, for example, the stability of heat pumps and how they operate. They are quite sensitive to fluctuating, for example, energy flows and these type of things. So is that also an area of research that you're considering? Because you want to have them operating in a robust way and also to start them up, for example.
Yes, this is a very important research area because reliability and stability is one of the top needs of this machine of these processes. Definitely, there are several control strategies for a heat pump to optimize the stability. So the compressors, they are running at, they can be run in part load operation, for example, to adapt to the need. Then typically they have secondary loops. So it's a question, what is really the media that is going into the dryer? Is it a pressurized hot water typically, or I don't know, some direct heat exchange to the air and so on. So the reliability and stability depends also, especially on this control. And to be honest, there is not so much information available at high temperature. Heat pumps are integrated since many years in dryers, like better than me probably, food dryers. Fruit dryers or timber dryers in the forest, wood industry, and so on. But at the lower temperature levels and probably these higher temperatures and probably also the larger capacities that are needed, these are major challenges. It's a good point. I'm a researcher, so we have here only small lab scale machines, and we published actually recently some data on how quickly a heat pump can adapt to the fluctuations. And there's a question also on this is a question also of the compressor technology. So there we have typically there are piston compressors or screw or centrifugal, turbo, and so on, and they have different behaviors in terms of fluctuation. Here we have seen piston compressors. They are quite let's say efficient also in part load operation. They are quite robust, and you have seen parallel arrangements, so several units in parallel. If you would go to then a very large heat pump for a 10 megawatt spray dryer, then they would rather use then centrifugal compressors, and then they have different control strategy. At the moment, there are not many such installations. Actually, it's only a very few, and probably GA is one of the let's say leaders in this sector.
Yeah, thank you very much. It's really a technology in development. So in that sense, yeah.
Thank you. So I think maybe we can summarize the whole event. I would like to thank you, thank all of the participants and especially speakers for joining us and accepting my invitation. We could see that actually I think there are two main reasons why we are all busy. So it is this energy consumption in spray drying and also the stickiness. So the stickiness has to be also always taken into account. But please remember, the list of modifications is not closed here. We were talking about 4 of them, but I can find many more. I don't know, maybe in the future we'll have another event to talk about, for instance, electrostatic spray drying, pulse combustion, foam, flame spray drying. There are many more different solutions. So I wish you good luck in your research. I hope to see your name in the list when I search for spray drying publications in Google Scholar. And thank you again. I think Maarten wants to also to add something about some conferences which will be organized soon.
Yes. Yeah, I think you see my screen almost. Yeah. Yeah, so also thank you very much on my behalf for participating in this great webinar and spotlight talk. Yeah, focusing on different types of spray drying. That was really interesting. Just on behalf of the EFCE Working Party, I would like to point out that we also have a very active LinkedIn channel. If you use the QR code here, you can actually join this LinkedIn channel where we will inform you about future spotlight talks, but also about other interesting opportunities and events related to drying technology, which are organized on behalf of EFCE Working Party Drying. And also would like to point out that there are 2 major events coming up. The first one is the International Drying Symposium in Paris. I think over 300 abstracts have been received. So there will be many participants in that event. So I'm really looking forward. It's in August this year. And of course, Eurodrying, that will be organized by our colleagues in Magdeburg. And they will organize it in July 2027. The exact dates are not yet known, to me at least. Maybe the organizers will announce them soon, and I'm also looking forward to that event. But it's in 1 year, of course. And if you want to have more information about the Working Party Drying, please visit our website. I think that concludes on my behalf. I don't know if someone else wants to say something. Then, I think we can round off and thank everyone for their participation and wish you a very nice day and good weekend.
Thank you, everybody.
Thank you.
Thank you.
Thank you.
Thanks.
Thank you.